So I was at a conference in Baltimore recently. A governor, like the first governor of the state of Victoria in Australia, and Latrobe is actually an Englishman, but his cousin was actually one of the first governors of Baltimore. And so when I was in Baltimore, I'm like, why are there so many signs with Latrobe as the name? And it turns out that, you know, like, that's just a pair of cousins. Yeah.
So they really had it in their blood, huh? It's kind of a French inspiration, like Latrobe is probably not.
I think it's like a corrupted French name.
Yeah, exactly.
Yeah.
I would have gone for Italian.
Yeah.
That little.
It's like a name of a French criminal, maybe.
Yeah.
I'm speaking English because our speaker today is an Anglophone and only speaks English. So it's our pleasure to have a chance to get Dr. Hien and Nguyen to present some of his work today. So I know Hien through a colleague of mine, Nguyen, who's Australian. So it makes for a very difficult communication because between my French accent and his Australian accent, it's always very interesting game of, like, you know, not understanding each other. But I became friends with him nonetheless, and when he moved back to Australia, he just contacted me about this, you know, Hien. I didn't know at the time, and it turned out that Hien is like a very unusual breed of statistician. It's a statistician who actually cares about data. And makes this effort to you know, spend time with people who are outside of his field to understand what they're trying to do. And so Hien came last year for a month.
2 years ago.
2 years ago? My God, time flies.
I know.
And you know, we planted a couple seeds for collaboration, but you know, it's at the end of the day not that long for a stay. And now it's back, and I feel like we're making progress.
Yep.
And we, in the meantime, we get the paper. So anyway, enough said about the presentation. So now, just Hien is an independent investigator in Melbourne, Australia,
yes,
and continues doing, you know, actual statistics, being a statistician, and also developing a lot of application in different fields, including brain imaging.
All right.
So,
thank you very much, Pierre, for the kind introduction. So the talk today is a little bit technical, but at the end of the day, it has a very neuroimaging kind of application to it, and that's the example that I'm going to be using to demonstrate the features of the methodology that I'm going to present. So the talk is about false discovery rate control, which is something I guess you got to deal with a lot in neuroimaging, and under rounding of p-values, which apparently is a problem that occurs more often than you'd think, and we'll see an actual situation where it occurs in the sequel. So the talk, I've got to acknowledge my co-authors. The talk is about work that we've submitted as a paper to the Scandinavian Journal of Statistics, and it's work with Johan Yi from the University of Toronto, which is Jason Lurch's PhD student, and he's at the Toronto Hospital for Sick Children, and also with my PhD supervisor, Jeffrey McLaughlin, as well. Okay, so let's start with some technicalities, because if we're going to be talking about p-values, we're going to be talking about hypothesis testing. If we're going to be talking about hypothesis testing, we really want to be sure we know what it is that we're talking about. So largely this you can ignore, but I just want to characterize what it means to conduct a hypothesis test. So when you're conducting a hypothesis test, what you're saying is that you've got some data, D for data, and that data comes from some known probability distribution. So for example, a normal space, a t-space, whatever it is that you want, and that probability model is going to be called P of theta, where theta is the parameter that you're interested in. So you're hypothesizing that the true parameter that generates your model is some theta naught, naught for the null, and that belongs to some set. And then you're saying that if it's not the null, then it's the alternative. And the alternative is just the set that contains the null, the set that contains all of your possible parameters, minus out the set that contains the null. And then a hypothesis test is just a rule, let's call it rho of the data. So you take the data, you compute a rule based on the data, and that rule outputs either a 0 or a 1. And that rule is based on some test statistic, T for test. Okay, and what you want to say is that you want to characterize the rule by some rejection region, R of alpha, R for rejection region, where alpha is your usual significance level, such that a rejection defined by the rule equaling 1 for rejection, is the same thing as your test statistic being in your rejection region. So for example, if you've got a normal hypothesis test and the rejection region is being outside, deep in your tails of your normal distribution, far away, many standard deviations away, and that's the same thing as saying that you're rejecting your null hypothesis. So it's an intuitive concept. It's maybe a bit technical when it's presented in this way, but it is exactly what the hypothesis test is that you're used to. Okay, so we say that rho is a rejection, and when we construct a hypothesis test, we're allowed to determine this region here, the rejection region, based on some alpha, which is our significance level, and that determines our type 1 error, which is the probability of a rejection given that our null hypothesis is true. So it's a probability of getting a false positive. So we control the probability of a false positive. Okay, so from the definition of a hypothesis test, we get our usual tool for conducting hypotheses that, for better or worse, is what we have, and that's the p-value. So the definition of a p-value is this. You got your p-value is the smallest alpha such that it gives you the largest test statistic, the largest probability of your test statistic belonging to your region of rejection. So this is just definitional. It is exactly what you do when you're conducting a hypothesis test. It's you calculate the area to the left and the right of your normal tail, for example. It's the probability of getting a result that is as extreme or more extreme than the test statistic that you got. The reason why I give the full definition is so that we're completely clear when I actually give these two sets of results, which are kind of the key foundations of what traditional false discovery rate theory is based on. And these two results, which you can find in Descartes 2014, which is a great book on hypothesis testing. The two facts that we have about hypothesis testing are thus. If we have some level of alpha that is a fixed significance level, and that bit is a technicality, then the probability, then you have this duality here. Your rejection is the same thing as having a p-value less than your level of alpha, and that's the usual concept of hypothesis testing that we use. When you have a rejection, you say that you reject the hypothesis if your p-value is less than alpha. And that's the duality that we use, and that's based on the definitions that we had on the previous page. And proposition 2, which is kind of the more important proposition that we have, is that if I have a simple hypothesis, that is, my hypothesis is that I have a single value of theta. For example, my mean is equal to 0, or something like that in a traditional hypothesis test. I test my mean is equal to 0 versus my mean is different from 0. Then under small list of regularity conditions, my p-value has a uniform distribution when I plug in random data. So if I repeat a null hypothesis experiment over and over again, I take the histogram, I should just get something that looks like a rectangle. Okay, so in modern hypothesis testing, such as in genetics, proteomics, and neuroimaging, we're conducting thousands to millions of simultaneous hypothesis tests at a time. Okay, so if we have DI as being realizations of data, big DI, and we have N as being the number of hypothesis tests that we're taking, and each of these hypothesis tests are simple hypothesis tests, then assuming that all of the hypotheses are null, our expected number of rejections based on the previous propositions is just our level of significance that we've set multiplied by the number of hypotheses that we're testing. And so, for example, if we have 1 million hypothesis tests, then on average, even if everything is null, we're still making 50,000 rejections, 50,000 totally erroneous false positives. And this is the problem that faces us when we're conducting large-scale hypothesis tests. This is exactly what we want to mitigate against. And of course, in neuroimaging, the consequences are clear. There's this very famous poster that was presented by Bennett et al. In 2009. It got a lot of press. Effectively, they put a dead salmon through an MR scanner. And they found neurological signals without false discovery control. And the point was that a lot of papers at the time weren't doing false discovery rate control and reporting their results. So obviously, if a dead salmon can have neurological signals, what does that say about all of the papers that weren't controlling for their FDR?
Well, hold on a minute. They asked the salmon to look at faces that were like happy or sad, and to tell if they could tell the emotions. So we don't really know, you know.
Yeah, well, maybe the dead salmon could. I'm not sure.
The fact he was dead is probably.
I think the fact that it was dead means that it's not gonna. I think you could probably use a control salmon that doesn't look at faces, Pierre, and you'd probably find similar results. Anyway, that's a technicality.
But here, this was not false discovery rate. This was uncorrected. This
Yeah.
was P001 uncorrected.
Yeah, but I mean uncorrected, you know, being not
but
correcting
I think
for
you
false
said
discovery
FDR.
or not correcting for anything, you know, just completely uncorrected.
Mm-hmm.
Yeah. Okay, so results such as, you know, getting signals from dead salmons forces us to consider how is it that we can mitigate against not false discovery, but we mitigate against these large-scale numbers of false positives. And one way of doing so is with the idea of false discovery rate control. And false discovery rate control was made famous by the paper by Benhamini and Hochberg in 1995, which I think is now probably the most highly cited paper in statistics. And it very nearly wasn't a paper. They were rejected for years until they actually got someone to take them seriously as a concept, because back then people were like, oh, well, why do you need this? We don't conduct that many hypothesis tests at once. Turns out we do. So yeah, the idea of false discovery rate control. So the idea of false discovery rate control is simple. All you're controlling is this FDR term, which is the expected number of false positives you make as an average of the number of rejections that you make. So it's the average number of false positives per rejection. And then this bit here multiplied by the probability of you actually making a single rejection at all is a bit of a technicality. But false discovery rate control works pretty much the same as your usual significance level control. You set a level, I'm going to call it beta instead of alpha, and then with that level, you then see how many hypotheses you reject rather than you setting a level alpha and seeing how many hypotheses you reject that way. Okay, so although the original paper of Benhamini and Hochberg is fantastic, the mathematics is fantastic, it's hard to fault it for its kind of given purpose and at the time being the first paper on the issue. The continual use of the method of Benhamini and Hochberg and its various evolutions, such as the Benhamini-Yekitieli paper, which allows you to do Benhamini-Hochberg on slightly correlated data, rely heavily on that second fact about hypothesis testing that I presented, which is the uniformity of the p-values under the null hypothesis. And as Efron in his book on large-scale inference from 2010 pointed out in chapter 6, which is actually a great read. I think that if any of you are doing any amount of large-scale testing, that's a really good chapter, and Efron writes beautifully. He points out that this assumption of uniformity is often violated. I mean, it's so violatable and so easy to violate that you shouldn't even be considering it in practice. And his three main points about how easy it is to violate are these. Firstly, you can easily have a complete failure of mathematical assumptions. I mean, often we use asymptotic results to conduct inference in neuroimaging. For example, we conduct a t-test, but because for some reason or other we compute the statistic or compute the probability with a normal distribution or something like that, and even that will skew your distribution of your p-value. Model misspecification is a key one. You can't include every possible covariate that you care about in your model, and every single covariate that you leave out is going to corrupt your hypothesis null in some way. For example, if you leave out some covariate, maybe your null hypothesis that you're testing about beta being 0, beta under the null might instead be 0.5. And that testing for 0 when it's in fact 0.5, that's going to obviously corrupt your null distribution from normality as well. And it also turns out that although even under uniformity, if you have correlations between your p-value and you collect up all the p-values, you're going to have a deflated variability, a deflated variance of your p-value than you would ordinarily get if you have independent hypothesis tests and you collect up the independent hypothesis p-values. So there are plenty of reasons as to why you might not have your uniformity assumption being met. And so you probably should use something other than uniformity. And so the suggestion of Efron is to use an empirical Bayes setup. So I know that a lot of people might be Bayesian. I don't want to do Bayesian. Bayesianism is subjective. Well, empirical Bayes is not Bayes. Empirical Bayes is purely frequentist. It's no subjectivity. Okay, so for the empirical Bayes setup, we have the following. So for example, let's suppose that we have a p-value, pi, and suppose that pi is uniformly distributed, just for the sake of argument to start off with. Okay, then if I take a Z transformation, which is just 1 minus the probability and then the probit transformation, then under uniformity, I should get the normal distribution back, standard normal distribution back. And so under the null hypothesis of all of my p-values being uniform, I should get a collection of these Z scores being from a standard normal distribution. So then if I have instead a null hypothesis that perhaps the p-value distribution is not quite uniform, then what I can suggest instead is that if it's not quite uniform, then perhaps the normal distribution will be close to the standard normal, but not exactly the standard normal distribution for my null distribution. So instead of a normal 0, 1 for my Z-score distribution, perhaps the mean of my Z-score distribution to the null is some value close to 0, and I'm allowed to vary the variance a little bit so that it fits better to what the true null hypothesis distribution is. Okay, so now suppose that our sample of p-values arises from both insignificant and null hypotheses and significant non-null hypothesis tests. And suppose that the proportion that they're split into is that you've got pi naught insignificant test, pi 1 significant test, and of course the proportion should add up to be equal to 1. Okay, so assume that the p-value from a significant test is smaller than the p-value from an insignificant test, right? That's a pretty fair assumption to make because it's going to be closer to 0. So then, if I do the Z-score computation, then the p-value being smaller under a significant test means that the mean of my normal distribution for my z-score for the significant result will be shifted to the right of the distribution, and I'll allow for the significant results also to have some kind of a variance that models their distribution as well. So you've got two distributions now. You've got a null distribution, which is to the left of your alternative distribution. And those two distributions characterize the entirety of your set of hypotheses. Okay, so let's go over it again. So what we have is that for each z-score, we have some latent variable Si that characterizes the significance of that z-score. So if so it's insignificant with probability 0, and it's significant with probability pi 1. And given that it's significant or insignificant, it comes from a normal distribution. And so what you end up with is that by the law of total probabilities, you have a probability density function for your entire set of z-scores, that is this two-component normal mixture model. You got the insignificant component and the significant component. And we call this model here, this is the empirical Bayes model of your z-score of your p-values. And so I'm just going to call theta as being the collection of parameters that characterize that model that we have. So just to visualize, this is what your model looks like. Right? You got your insignificant component in blue, you got your significant component in red, and the overall black line is, say, your total distribution of your p-values. Not your p-values, your z-scores. Yes.
Is that okay to interrupt you?
Yeah, sure.
Are you in practice diagnosing this? Like when you apply this method, are you actually making a histogram of p-value and seeing if it's like looks like a two-component mixture model? And
yeah,
you
absolutely.
Sometimes extend that with like 3.
Yeah, you totally could, but it looks like in most cases 2 components works very well.
Yeah.
Yeah. Yeah. Yeah, you could definitely have 3 components. Your null or your alternative distribution could be non-normal, like a skewed distribution or whatever. It's there's a lot of variation on this.
Because when you have the GLM connectome pipeline, you actually load the p-values, they're in there, and you get exactly those kind of histogram. It does really look like basically one normal distribution with a skewed tail on one side, typically.
Yeah, you can definitely do that. Okay. All right, so back to some technical stuff. So using our empirical Bayes model, we can control for, we can compute an empirical version of what I'm going to call the marginal false discovery rate, which looks like the false discovery rate, but obviously isn't quite, because the false discovery rate would be the expectation around both things, and now I've got the expectation of one thing divided by the expectation of the other thing. So why do we control the marginal false discovery rate? Well, because using our output from our empirical Bayes model, or the parameters from our empirical Bayes model, it's really easy to estimate the marginal false discovery rate from any particular set of data. If we have a set of data, Zi, then we can compute this term here, which estimates the marginal false discovery rate using this estimator for our rule here based on these assignment probabilities that I'm not going to go too much into. It's just know that it's actually really easy to estimate. Okay, but that still leaves us fairly unsatisfied. So I can control this guy, I can control this marginal false discovery rate, but does that even mean that I'm controlling my false discovery rate? Well, we've got 2 nice little hypotheses that says that this is okay. 2 nice theorems that says that this is okay. So the first theorem is this one here. So if I define a sequence of stuff that is indexed by I to be M-dependent, M-dependent meaning that any particular observation is only dependent on, at most, m, where m is a finite number other observations. So not independence, but also not allowing for an observation to be dependent on everything else. You know, it's a reasonable halfway point of dependency. If I have m dependence, then in my 2014 paper, I proved this nice little result here, that if these two guys are constant, and my sequence is both stationary and m dependent, then that estimate for marginal false discovery rate goes towards the marginal false discovery rate. So the estimate goes towards the true object in probability. And nicely enough, under m dependence and the same two assumptions as I had previously, numerically, as I get more and more observations, more and more voxels or whatever in my image, my marginal false discovery rate actually goes towards my false discovery rate. So controlling the marginal false discovery rate in a sample that's big enough is the same thing as controlling the false discovery rate. So we have what we need to have. Empirical Bayes allows you to control the false discovery rate, at least asymptotically.
Asymptotically regarding what?
Regarding the number of voxels that you have, yeah.
So you can compute that and you see the thing, like
yeah, you can compute,
but you don't know to what it.
Well, you don't know what these true values are
exactly,
anyway.
yeah.
So but theoretically, you're controlling the same thing as you get more and more observations.
I get a random question again.
Yeah.
I know with the FDRs, there's like this issue that, you know, in imaging often we don't conduct a single experiment. You know, we're going to test many contrasts, and we are going to typically correct for multiple comparison for each contrast we run, but not for the number of contrasts we run.
Mm-hmm.
And then there was this whole discussion whether, you know, if you control for the FDR, for each contrast, the FDR kind of being a proportion, maybe it would scale and you control for the FDR overall. And it's not completely clear, and I haven't found like good theoretical results on that. Benjamini actually published a paper on that. You end up with like having very severe FDR threshold for each contrast, so you actually have a price to pay. Would that MFDR scale across maps? Have you thought about that? Because I know I tried to work on it theoretically, and the fact that the expectation is around the fraction instead of being at the numerator and denominator was an issue.
It should. I can't see a reason why, because it's.
Because that's why my 2015 paper got rejected.
Yeah, right. Because as long as you fit the distributions, the same proportion of hypotheses should be rejected each time. Yeah. It should be, the proportion of rejection should be the same. The proportion of rejection shouldn't be decreasing with n. Yeah.
So we should maybe start using MFDR for everything.
Maybe. All right. So estimation. Not a very important slide, this one. All it says is that you can estimate it using the framework of maximum marginal likelihood estimation. So you'd all be familiar with maximum likelihood estimation. Maximum marginal likelihood just means that I'm ignoring the inter hypothesis correlation. It turns out that under M dependence, this is perfectly fine. You still get consistent estimators for your parameters, and because this is just a basic two-component normal mixture model estimation problem, you can just use the EM algorithm, and you can look at Jeff's book on the mixture models to look at the EM algorithm for the estimation in this situation here. Yeah, so you can estimate it. If you have the data, you can estimate it. So let's have a go at some actual data analysis. So let's have a look at some neuroimaging data. So a popular paradigm in neuroimaging is the notion of the connectome. I don't think I have to tell this group about anything about the connectome. It's a map of connectivity, causal relationships, and brain regions of interest. So one approach of connectomics is to use structural covariance, and that's very much championed by Jason Lurch, where he uses deformation fields. And what he does is he registers all of the image from a population to some average model, and then from the registration to the average model, it computes the Jacobian of the deformation, so how much the image had to change to make it look like the average image at each of the voxels. And then for some particular region of interest that he wants to find out whether or not it influences the rest of the brain, calling it the seed, you look at the correlation between the log determinant of that particular seed location towards every other voxel in the brain in terms of the log determinant of the Jacobians. And then you conduct the hypothesis test to see if that particular region is correlated with every other particular region of the brain of interest. So every single voxel. So in the example that we have a mouse imaging data example that's processed in the Lurch 2010 pipeline, and the example is of a 241 adult male and female mice brain that were taken from the control group from the Eligood 2015 paper. So all of these references will be in the end of the slides, and I'll put these slides online. So don't worry too much if you don't know what Eligood et al. 2015 is. I don't either. So the mice were each scanned using a 7T scanner, T2 weighted images, and what was acquired was a 225 by 320 by 152 voxel image, of which around 2.8 million are actually brain matter. And after registration, the Pearson correlation between the seed voxels log Jacobians to a seed was computed towards every other voxel, and that was in the bed nucleus of the stria terminalis. I don't know what that is. Can you tell me what that does? Someone tell me what that does later. Yeah, and so...
It's really an exotic one. Like, does anybody ever heard about this?
Yeah. I know the word bed and the word nucleus, and I know the word terminalis. I don't know what they mean altogether.
Maybe it's a mouse thing. Because that's not human data.
Yeah.
No, it's human. It exists in human too.
If it's in the mouse, it's in the human too.
Yeah.
So.
But anyway, we conduct these hypothesis tests using Pearson correlations and using the hypothesis test method by taking Fisher's Z transformations and computing the Z statistic based on that. So you can already see that it would take, using Z statistic, we're using some kind of an asymptotic test, and if we're using some kind of an asymptotic test, then we probably have some violation of mathematical assumptions. So this is why it's a good situation for empirical Bayes. Yeah, so here's the histogram of significance. So we can see that a lot of p-values are close to 0. And the log square of the transformation, so there's a lot in the tail, so that means that there's a lot of significant results going on here, or at least a lot of high effect sizes. And here's the map of the p-values. So red being smaller p-values, blue being larger p-values, and that's the structure of the brain. So we can see lots of significant results pretty much everywhere, really. Can't really tell. Not sure what's going on in the blue areas, but they form really nice patterns. I like them. It's very artistic. Anyways, the really interesting thing about this data set is as follows. From the 2.8 million p-values that we have, for some reason there's only around 66,000 unique different values.
What's the precision on the estimate?
I don't know. But effectively, it doesn't matter what the precision is, you've got rounding, right? That's like a clear indication that you've got some kind of rounding of these p-values going on. And from the computations, because some of these p-values are exactly 0 from rounding and exactly 1 from rounding, you get infinite z-scores because you're taking like log transformations, right?
And it's
the z-scores.
It's not even that bad. Like when you do permutation testing in FSL or whatever, you know, if you do 1,000 permutation, you have 1,000 distinct values. You know, it's discrete p-values.
Yeah, it's very common, I suppose. But I mean, this is surprising because they do continuous tests. Yeah. So you only have around 66,000 unique values, of which 300,000 are p-values of 0. 6 are p-values of exactly 1, and we don't care about those guys. So it looks like from this complex multi-stage analysis pipeline, we're getting some kind of rounding, and the rounding puts the p-values on a grid of somewhere between 2 to the 16 to 2 to the 17 unique values. So what happens when we have to deal with this data with our empirical Bayes model? Well, this is what the histogram of the z-scores look like if we ignore the infinite values. So we can see that infinity starts from about 4.5 or something. You know, 4.5 is hardly infinity.
So that means that any z-value above 4 would be mapped to exactly 0.
Yeah, mapped to it, yeah. And if we were to just ignore the infinite z-scores and fit our two-component mixture for our empirical Bayes model, we get it very wrong. Yeah. We know that there should be a tail that trails off over here. But obviously, the model doesn't know that because we don't have those infinite values to take into account that tail. Okay, so obviously we have to account for this somehow. So the nicest way of accounting for it, of accounting for rounded data, is actually to just double down and round it some more, really. So what we're going to do is, hey, you might think that that's a dumb idea, but it works. So what we're going to do is we're going to declare a binning of the data. So a binning of the data is just going to be m points where we partition our space, our real line, into m intervals. And for each observation, we're just going to put each of our z-scores into one of the bins on our real interval. Okay, so that's all this is saying here. We're putting the z-score into one of the bins, and in the end we get this new random variable x, which has a 1 exactly where our z-score lies on the real line in the bins, and a 0 everywhere else where it doesn't lie in terms of the binning. Okay, so it turns out that if we do this binning, then the log marginal likelihood function that we can use to conduct maximum marginal likelihood estimation is actually really easily written out. It's just the sum over the bin bits summed over the number of observations, where the only really interesting thing here is this integral that we have to care about, where we have to integrate over the binning. But it turns out, nicely enough for me, that Jeff has solved this problem for me on the year I was born. So he gave me kind of a nice birthday that I only got to open when I wrote this paper. And so his birthday present to me was this guy, which is the E step to his EM algorithm, this guy, which is the M step to his EM algorithm. And in the end, you get, I know that it looks like a lot of equations, but it's actually quite an elegant procedure of estimating based on this binned data. And I won't go through it because it's unnecessary to go through. But just know that there is a very elegant estimation procedure that you can put all this through. And the other nice thing about binning is that you discretize your data. And Seo and Lindsay, in their 2013 paper, were able to prove that if you had discretized data, then any kind of maximum likelihood estimator of discretized data is almost universally consistent. So you almost universally can estimate the true parameters back from discretized data. And I go one step further. I just modified the CO and Lindsay result because all the result relied on, I mean, it's a bunch of math, and then in the middle somewhere you got a law of large numbers that depends on independence. You just replace the law of large numbers that depend on independence with a law of large numbers that depends on M dependence. And you get the fact that if you have M dependent data, then discretized M dependent data is almost universally consistent. You can almost universally always get your correct model back. Which means that our model is a discretized model, and so we can almost always universally get back our true parameters from our data. Okay, so some practical considerations. Well, we're talking about a binning, but which binning? You know, you can always bin using different schemes. And there's a million different schemes that you can use. A lot of these schemes come from non-parametric estimation theory, which is how to build histograms. And the oldest work kind of on how to build histogram is the work by Sturgis in 1926, and he just says, well, just take the number of bins to be log 2 of the number of observations you have plus 1. Seems to work fine. Seems to work fine for us. There are more sophisticated methods, but it actually turns out that Sturgis' method actually works among the best compared to the more sophisticated ones. And another piece of serendipity for me is that turns out that someone's already implemented most of this for me already. In terms of the algorithm part of things, and so this McDonald and Dew paper in 2012 implemented effectively the EM algorithm that Jeff deduced back in '88 in this package called MDist that's implemented in R. And McDonald is a Canadian guy who works in fisheries, so that's my Canadian plug. Okay, so if we now use the binning strategy and we estimate the distribution again, this is what we get. So this is the correctly fitted empirical Bayes model. So again, the blue bit is our null bit, the red bit is our alternate bit, and we can see that now we actually estimate correctly the tail, where it should drag out, it does drag out. Yeah.
I mean, I think you mentioned it, but I'm not sure what you've binned there. That's what
I've binned the Z-scores.
So the Z-score.
The Z-scores are now in histograms.
Yeah.
Effectively.
But then what I see is like you have a lot of the zeros, but then how do you control the binning around zero?
Oh yeah, so the zero is just, you put it into one big bin that drags on to infinity.
Then you don't control the size of that bin because the cutoff is at 4.
Yeah, so all the other bins are uniformly shaped. But then the last bin just extends off to one side, and the first bin just extends on the other side.
So, and that lets you, yeah, but that's what I understand. But yeah, well, I would need to see that. So the width of the bin.
Oh, you can have varying width bins.
And it has no problem.
It has no problem with that. Yeah.
Okay.
And how do you decide the number of bins? Or
I use Sturgis' method.
Okay.
Yeah, but you can use anything. You can use any kind of histogramming method or anything like that. In fact, these are the Sturgis bins. So you can imagine that there's one bin that just drags out this way, and there's another bin that drags out that way, and all the other data are binned inside of these histograms. These histogram bars, rather. Yeah, so we end up with a much more sensible model. Using this, we get the tail that we wanted to get. I mean, it doesn't fit perfectly because we're using two normal distributions. Perhaps that's what you're getting at, Pierre, but it fits well enough for us to conduct reasonable inference.
But do you need actually to fit the middle of your distribution? Like basically the
yeah, you're right. That's the tail. That's the most important bit. Absolutely.
But so again, what's interesting is that basically your blue distribution here is your null.
Yeah.
And it's not centered on 0 because
yeah.
it's a parameter you're giving.
Yeah.
So in effect, you're not really detecting, non-zero correlation. You're detecting correlations that stand out from the background, essentially.
Effectively, yeah.
So it's kind of more of an outlier detection method.
But I mean, like as I said before, my mathematical assumptions might be wrong, and
Well, I think it's a very nice property.
Yeah.
Like something we get a lot in brain imaging of fMRIs, that we are going to compare groups that don't move as much one than the other, and that can create sort of like pervasive differences all over the brain. And depending on how you pre-process those data, you may actually exacerbate those differences for very like distributed effects.
Yeah.
So I think actually having a model that built-in try to find like what stands out,
yeah. Well,
as opposed
that's
to a background effect, may actually be more robust to those.
well. I guess that
decisions.
comes back to what I was talking about. Like it's what you define as significant and insignificant, right? Significant being something that is kind of just ordinary. Oh, no, not ordinary, right? Yeah.
Really like the idea, but it's just like in my head around like what
Yeah.
you're proposing.
Yeah, well, that's a very good interpretation of it.
But I think like melodic statistics, like the ICN FSL works exactly like that. It's a mixture model.
Yeah. Oh, it's a very common framework for thinking about hypothesis testing, but it's the estimation that's interesting for me. Yeah, so these are the two fitted distributions for the empirical Bayes model. So here's the outcome that we get. So it turns out that around 50% of the voxels may be significant or non-ordinary. And the null distribution, as Pierre rightly pointed out, is shifted slightly to the right, which kind of indicates that null hypotheses aren't quite exactly uniform in their p-values. And if we control at the 0.1 level of false discovery rate, we get around 600,000 voxels, which is around 21% of the overall brain volume. And so if we map the p-values again versus the things that were controlled at the 10% level of false discovery rate, these are the regions that we find are most varying. So, I mean, it's not too much of a stretch of the imagination to believe that, the overall size of the brain is probably one of the most varying bits regardless of what you're testing against. So it's not too surprising that a lot of the variability of the rejected regions are around the sides, and I've been told, at least by Jason and Johan, that this is a reasonable biological outcome for what we're looking at. Again, I don't know what the bed nucleus is. Yeah, and so that's pretty much it. That's pretty much the talk. There's a lot of further work to be done. There's a million comparisons that we can do to other methodologies. So I don't really know if that first one is really future worth. It's future worth for an honors student or PhD student maybe. But we can also investigate better binning techniques, which is what you were asking about, Christian, because we can of course do non-uniform binning, adaptive binning, lots of potential there. Right now we're binning first and then we're estimating afterwards. There might be some way of doing both at once that could make the procedure even more adaptive. And as you were getting at, Pierre, the null distribution doesn't necessarily have to be normal. It can be two normal distributions. It could be a skewed distribution. It could really be anything. Its model is like very modular in the way that you implement it. It comes down to a bit of what assumptions you're willing to make, but it's very modular. And I think that given good data, you can fit very nice adaptive models to your data that allows you to make much more powerful inference than your standard false discovery rate procedures allow you to do. Okay, so bunch of references for you guys. Of course, I'll put this up on my website. So thank you very much for listening to my talk.
a lot, Hien. Is there any question on the formulas, maybe?
No, don't question the formulas. Just I thought I'd put this up on archive, but obviously I hadn't. So email me if you want a copy of the manuscript.
Thank you.
So, just a quick one, and I mean, we already had a few exchanges during the talk, but basically my understanding, one of the main tricks you said there's rounding errors in the p-values, but those rounding errors are not going to necessarily impact an histogram of the p-values too much. So I'm going to translate those, continuous values to a histogram and roll with that, and hopefully the rounding error won't have too much impact.
Yeah.
Have you actually checked that?
Yeah, I have.
Okay.
Yeah, so that I've done some extensive simulations on that.
So what type of simulations?
Simulation versus various degree of rounding, and whether or not you get better, more consistent estimates, or more accurate estimates of your true generated parameters versus greater and greater degrees of rounding.
Okay.
Yeah.
Because so one of the issues we have with the FDR procedure is that it's pretty finicky. It's like the proportion of discoveries are going to change quite a bit with even like minor perturbation of the data. And that's really in your face when you do non-parametric p-values. Because if you don't control for your random seed, you just rerun a new set of samples.
Every time you do it, you get some coming out.
And the p-values may not change a huge lot, but the result of the FDR procedure, if you don't get those zero p-values, they're going to drive everything or very close to zero. The procedure can completely fall down. So have you checked that, whether if you use some kind of like non-parametric test to get the p-value, your procedure would be?
I haven't tested against non-parametric tests.
Because
I've only tested against rounding and parametric tests. Yeah.
And it's becoming increasingly used.
Yeah.
In brain imaging, there's like a group, Tom Nichols and Eklund, pushing very strongly for non-parametrics. And I don't think that the FDR procedures that are being used or whatever, because they have the TFC procedure, whatever it is, have been really evaluated in terms of the stability.
Yeah, right.
Against the number of.
Yeah, but I think you're right that because of the rounding, you do get more stability because you only usually get p-values wobbling around certain regions, right? And so if you bin it the same way every time, then they should usually bin into the same areas every time. Yeah.
So he couldn't make it today, but Tristan Glata from Contrôle University is very interested in the numerical robustness of pipeline, and he's trying to nail down every step of our complex pipeline and see what's robust, what's not, and how we can make it more robust. So I think he's going to be very interested in trying that out.
Yeah.
In that sense.
Yeah. I mean, I've got codes if anyone wants them. It's just they're very specifically implemented on the mouse imaging data. So you'd have to be willing to play around with it.
Understood. All right. Okay. So thanks again.
Well, thank you for inviting me, Jeff.